Hello, my name is Sam, and I'm a member of the FTC team number 11454 from South Carolina called the Penguineers. I'm the main SolidWorks modeler on the engineering team, and I have quite a bit of experience creating assemblies to represent different designs. In this series, I will go over some basic skills needed to effectively use SolidWorks to create a design for your team's robot and to help prototype different ideas. First, I want to talk about some advantages and disadvantages of using SolidWorks or some other CAD software, such as AutoCAD or Onshape to create a robot design and first tech challenge. One of the main advantages of using computer-aided design is that it allows you to create a very detailed model of your team's robot down to the last screw and nut. This means that computer-aided design is pretty great if you want to make a very cohesive design. As you can essentially lay out the robot's design completely without sacrificing quality. Secondly, CAD allows you to make a detailed parts list of your completed design in order to make sure you have enough parts to build your design or purchase new parts without ordering excess. Lastly, this one is a bit technical, but some CAD softwares, especially SolidWorks, allow you to do partial or even full mechanical simulations of the robot's functions. If you're willing to invest enough time, you can use SolidWorks to simulate the rotation of motors, the interaction between multiple objects, and do finite element analysis to make sure your design holds up to stress well, and make improvements if it doesn't. Mechanical simulations essentially allow you to test a prototype without spending the time to build it, and then realize the mechanical failure after it's already been built. Although SolidWorks is pretty great, there are some aspects of it that are challenging for new users, which require some time to learn. SolidWorks essentially treats an assembly you make as a real object, so you can run into some problems if you don't put your designs together realistically within the software. Also, SolidWorks is pretty resource intensive, and since a license of it already costs about $100 yearly for the desktop student edition, it might end up being quite expensive to have the capability of using it. If you don't need the full functionality of mechanical simulation in large assemblies with realistic construction, then maybe consider another program, or use the cloud version of SolidWorks instead, which is $40 cheaper and offers a more approachable experience in addition to not needing a powerful computer to run. If you're willing to put in some effort though, you can usually find free sponsored versions of SolidWorks, and first actually link some of these in Game Manual 0, so be sure to check this out to save some money if you're a robotics team. Now that I've gone over that, let's talk about some basic aspects of using SolidWorks and what you can do with it. The main two capabilities of SolidWorks that are most essential for creating a robot design are sketching new parts and creating assemblies of parts. For example, while most of your robot's design will likely be made up of off-the-shelf parts from companies like Rev, AndyMark, or GoBuilda, you may decide that the best solution for a design problem on your robot uses a custom part or two. For example, our robot from 2 years ago had a custom 3D printed piece that we attached in order to attach a bucket mechanism to a custom linear slide we made. Usually, making only a few parts on your robot custom if they really need it is typically the best practice for teams that don't have huge manufacturing capabilities like access to multiple 3D printers or even metal machine tools like lathes and water jet cutters. Despite this, some ways of making custom parts are very simple and oftentimes necessary. Let me show you an example, coming from our first generation design of our robot that we had created over a weekend. Our Gen 1 design used a custom claw, which was made by bending two ends of two Tetrix plates and attaching some pieces of this grip enhancing material that came off of another product we had cut up. As you can see, the changes in game design make it very advantageous to use custom parts for when your robot has to intersect with a game piece, since they usually end up being a different shape, size, and weight every year. This model is the same one I went over from the example earlier. It is a simple Tetrix plate with both ends bent at an angle to create one half of the claw used on the Gen 1 robot design. In order to make this claw, I looked at the SolidWorks model of the real unmodified version of the plate and used some measurements that I took off of it with the Evaluate tool, which essentially acts as a multi-purpose digital measuring tape in order to replicate the original model's outer dimensions. This is one place where you should be very careful about the level of detail that you want to express in a conceptual drawing. In this example, I purposely left out the many medium and smaller holes that were common in the original model when I was making the modified version. This was due to a number of factors. Firstly, some of the holes that were present in the original model had a center point located exactly on the bend of the ends of the plate. In the real world, this was quite easy to do, and all we did to create this part was bend the ends by hand at roughly equal lengths away from the middle of the plate at both ends. In SolidWorks, however, it would have been unnecessary and wasteful to spend the time required to fully model the holes on the piece, as it would have increased the design's complexity by an order of magnitude to accomplish an unnecessary goal. This is just one example of how it's not always necessary to use full quality when making a model of a custom or modified part. However, there are a couple cases where it is necessary to do so, especially when the model you create will be used to manufacture the design in the real world. Whenever you are going to create a model using a machine, such as a 3D printer, you need to make sure you build the limitations of your chosen manufacturing mode into the model when you develop it. For example, it is much harder for a 3D printer to make sections of a part that are only supported by the sides and not the hot plate that the model rests on. Some other examples would be laser cutters, as most cutters capable of cutting through metal have very limited mobility and cannot move in the third dimension to create structures that have a useful height, leading to the most easy to make designs often being flat metal plates with holes and other features cut out of them. In the next couple of videos, I will be mainly going over how to create sketches, compare methods of making them, and how to make assemblies from both off-the-shelf and custom parts.